Good evening. Welcome to this presentation where I introduce to you how the pressure and temperature experienced by some metamorphic rocks a long time ago in geological history can be estimated using what is called classical thermobarometry. Classical thermobarometry depends on reactions. The idea being that if we know beforehand that certain pressure and temperature conditions are required for a certain reaction to occur, and all we find are the products of the reaction, then we can estimate that the system must have experienced such conditions that allowed the reactions to occur. An ideal thermometer is a reaction which occurs at the same temperature at all pressures. An ideal barometer, on the other hand, occurs at the same pressure at all temperatures. To understand which reactions are suitable thermometers and which are suitable barometers, we need to understand Gibbs free energy first. Let's do that now. Gibbs free energy can be thought of as the ability of a system to perform work on its surroundings without exchanging matter with it. Simply put, a system is more stable when it has the least Gibbs free energy possible. Gibbs free energy of a system varies as a function of temperature as well as pressure. The temperature axis on this diagram is for representative purposes only. It could have easily been pressure. Suppose that we have a system where two mineral assemblages are possible depending on the temperature of the system. The system can either have minerals A and B, or it can have minerals C and D. At low temperatures, the system is stable if it has the minerals A and B, since then it would have less Gibbs free energy. For the same reason, the assemblage C and D will be more stable at high temperatures. At some intermediate temperature, the Gibbs free energy of the two assemblages are equal. It is at this temperature that the reaction occurs. On a PT graph, the reaction line simply represents all the points where dG is 0. Although dG is shown to vary with temperature, as mentioned earlier, dG can also vary with pressure. The important thing to note here is that the reaction happens only when dG is 0. When dG is 0, a special relationship called the Clausius-Clapeyron equation becomes valid. It decides whether a reaction would make a good thermometer or a good barometer, or neither. The Clausius-Clapeyron equation gives the slope of a reaction on a PT graph as the ratio of the change in the entropy to the change in the volume after the reaction. If you recall, an ideal thermometer is a vertical line in PT space, and an ideal barometer is a horizontal line. If delta V is 0, dP by dt is infinite, and the reaction is a vertical line on a PT graph, this reaction would be a good thermometer. Exchange reactions make good thermometers. If delta V is much higher than delta S, dP by dt is close to 0, this reaction would be an ideal barometer, as then the reaction line would be horizontal. Net transfer reactions make good barometers. Net exchange reactions are reactions where two minerals exchange only a pair of ions between themselves. The two ions exchanged have very similar ionic radii, hence the changes in the volumes is very negligible, and this makes such reactions good thermometers. Let's look more closely at the exchange of iron and magnesium between garnet and biotite. This is a reaction where garnet and biotite exchange iron and magnesium between themselves to turn from almandine and phlocopite into pyropendanite. The ionic radii of Fe2+ and Mg2+ is very similar, and the manner in which they are packed in the two minerals, garnet and biotite, are not very different. Hence the change in the volume is very low. In a system containing only garnet and biotite, at low temperatures, all the iron is in the garnet and all the magnesium is in the biotite. As the temperature increases, iron goes to the biotite and Mg goes to the garnet. The important thing to note here is that the exchange happens over a range of temperatures and as a function of temperature itself. As a result, we can look at the fraction of Fe and Mg in the two minerals and hence estimate the temperature. Of course, we have to assume that for some reason the minerals did not exchange any ions during cooling since reaching that temperature. For example, if there wasn't enough fluid to allow the ions to diffuse. Now, these are some examples of popular geothermometers. You will notice that they are all exchange reactions where ions are exchanged as a function of temperature. A long list of geothermometers and barometers is given in J.D. Winter's excellent textbook Principles of Igneous and Metamorphic Petrology. Highly recommended. Now, these are reactions where some minerals react or break down to produce completely new minerals, hence the delta V may be large. We generally look for reactions where the change in the volume is large. One example is what is called the GASP barometer. GASP is an acronym made from the names of the minerals involved. G is for the calcium-rich variety of garnet, grossular. A is for Al2SiO5 in the form of kyanite, S for silica in the form of quartz, and P for plagioclase. As you can see, it is a reaction where the anorthosite portion of plagioclase breaks down to form the other minerals that I mentioned. Plagioclase exists as a mixture of the sodium-rich albite and calcium-rich anorthite. The breakdown of anorthite transfers calcium from plagioclase to the garnet, which itself exists as a mixture of grossular, almandine, pyrope, and spessartine. How much calcium is transferred to garnet to form grossular is a function of the pressure at which the reaction occurs. At low pressure, the proportion of calcium in plagioclase is far greater than the proportion of calcium in garnet. As the pressure increases, garnet becomes progressively richer in calcium and plagioclase becomes progressively poorer in calcium until we reach a point where the proportion of calcium in garnet and plagioclase is the same. Here are some other popular and well-calibrated geobarometers. They're all net transfer reactions. They're known by their acronyms which, like GASP, were created by the minerals which are involved in the reaction. Deriving a balanced reaction from the acronym alone is a fun exercise. In addition to exchange reactions, we can use the phenomenon of exsolution of minerals and that of homogenization of fluid inclusions to estimate past temperatures. I encourage you to look them up and also to look at the myriad of other ways in which past PT conditions of rocks and minerals can be calculated. Thank you.